Our first tool for transcendental functions, our first unit, is the derivative of inverse function. And here we'll give a little context for inverse functions by recalling a property that some functions have, which is called one-to-one. So generically, you can think of a function as being an input-output machine with a y value as its output and x value as its input. Domains represent what numbers you're allowed to plug into the input. So this example, I have the domains going to be all numbers between 2 to 5, not including 2 or 5. And the function I have here is f of x equals 3x plus 2. Okay, so this definition of one-to-one claims that if you have two output values that are not the same, that's what this notation means, two y values that are not the same, that guarantees that your input values have to also be different. And only one-to-one functions have that property. There's an equivalent way of saying it, that if in fact you can, for all x and y's you can imagine, if the two y values are the same, so you happen to know the two y values you're looking for, if they happen to be the same for all y values in the range, that must imply that the x values are also the same. So this second way of stating what a one-to-one function is equivalent to the first way I stated above here. And that gives a quick, easier way to algebraically check if your function's to one-to-one. So if we take a look at this example, I have an equation that I have a function described by an equation. And if I'm going to use this format, I would assume that the y values are the same without assuming that the x values are the same. And I'm doing this generically with any number inside the range. What I get is an equation I can set up and try solving. I would substitute x1 into my function, and if I do, I'd have a 3x1 plus a2 equals, and then I substitute my x2 inside the same function that goes on the other side of the equal sign, 3 times x2 plus a2. And then I would do my algebraic tricks of solving, which is, you minus the 2 from both sides. Okay, and then I divide, of course, 3 into both sides. So just by setting these two equations equal to each other, the two y values equal to each other, I get that the x values in all domains have to be equal to each other. That's how I know the function I wrote here is one-to-one, at least in an algebraic sense. So you can use the same technique to algebraically verify that a function is not one-to-one. So I have an example of another function here, x squared plus 2. And what I really do is set up the same kind of equation. Take my function, set it equal to each other, then substitute x1 into the left side and x2 into the equation right side in itself, and then I algebraically solve and see if I get the same thing for all choices of x. So I'm going to skip through the algebra here, at least to this step where I've got this. And the trick is I should take the square root of both sides. That's how I get rid of the square. And if you solve an equation by taking the square root, you have to remember there are two possible solutions, the positive solution and the negative solution. The same, so these two x values are exactly the same, or one is the negative of the other. And this is since we have two solutions, this function cannot be one-to-one. So the value of a one-to-one function is that if you know you have a one-to-one function, you can set up an equation like the problem up here, f of x equals b, and there's exactly one solution. Graphically, you could see that as saying that, well, when you want your y value to equal b, that represents a horizontal line that goes through wherever b is. And you have a picture of your one-to-one function. So it's this curve going like this. And it's claiming there's only one intersection. And so that's good to know that generically speaking, if you have a one-to-one function, there's one solution. That unique solution helps you solve some problems in a certain way sometimes. The horizontal line test is a nice theorem that graphically shows you what it means to be one-to-one. So in this picture, in this example, this curve right over here would be a one-to-one function, because if I draw any horizontal line, it only ever intersects the curves once. Well, if I take a look at this picture and I draw a horizontal line, it intersects the curves many, many times. So it cannot be one-to-one. So I'll say this one is not one-to-one, and this one is one-to-one. So setting your function equal to a single value will give you a single solution for the, it's unreasonable to expect every single common functions to be one-to-one. For example, this function is clearly not one-to-one because if I did the horizontal line test, the graph will intersect, say, a horizontal line many, many times. However, there's a trick to the definition. I can always restrict my domain to give me a one-to-one function. That means you can always find an interval in your graph that would pass the horizontal line test. So I can modify my function by just modifying the domain, restricting it from pi over 2 to 3 pi over 2. And if I do that, on just this little window or this little segment, I can see that in fact I do have a one-to-one function. If I go ahead and do a horizontal line, it doesn't matter where I draw it, at least in this little window of red lines, my blue curve is going to intersect that horizontal line only once. I can slide it up or down. It's only a single intersection point.